Okay, here's the first FRQ. We have here an RC circuit with two switches, and for part A, it says we need to use Kirchhoff's loop rule to derive, but not solve, a differential equation that can be used to find charge Q on the capacitor as a function of time after switch 1 is closed. And we have to express our answer in terms of Q, T, epsilon, which is the EMF of the battery, R1 and C. Well, here, what's going to happen is at time T equals 0, switch 2 is going to remain open, but switch 1 is going to be closed. All right, so we're going to close switch 1, and what we need to do is we need to use the loop rule to write down an equation to set up our differential equation, but you don't have to solve it for part I, only for part, or part 1, part 2, you have to solve for the equation. So let's draw a little loop here. I'm just choosing starting at the negative terminal of the battery. So starting at the negative terminal of the battery, we gain voltage equal to the EMF of the battery. EMF stands for electromotive force. It's basically the voltage of the battery. And here we're going to lose, so the current is going to flow in this direction. Okay, so we're going to have a voltage drop across resistor 1. All right, so it's going to be minus I times R1. And then here, the potential is going to drop again based on the potential across the capacitor. And we know that if Q is equal to C times V for a capacitor, then V is equal to Q over C. So whatever charge is on this capacitor, okay, the voltage is going to drop Q over C. All right, so then our final expression, we have epsilon minus I R1 minus Q over C equals 0. And to set up our differential equation, the way we're going to do it for this problem, we're going to do it in terms of dq over dt, right? Because we're going to try to find the charge Q on the capacitor. In the lesson that we had in class, we did it in terms of dv over dt, but you're going to see it's the same difference. So now I'm going to write I as dq over dt, because that's the definition of current. And then I have epsilon minus dq over dt times R1 minus Q over C equals 0. And that's your answer for part 1 of part A. Part 2, now we get to solve the differential equation. We have to derive an expression for Q as a function of time using the same quantities that are given. So now here, what we're going to want to do is we're going to want to separate our variables and integrate in order to find the solution to the differential equation. So here I'm going to get dq over dt by itself. So I have dq over dt times R1C. That has to equal C times E, or epsilon, but EMF of the battery, basically, minus Q. All right. So basically what I did was I multiplied everything by C, and then I just moved everything around to end up with this expression. All right. I'm going to have to simplify some steps because I don't have much space to work with here, but it's a good exercise. Try it out on your own first, see where you get stuck, and then see where you made an error in deriving the expression for Q as a function of time. So now what we can do is I'm just going to separate my variables. So now I'm going to get the dt over to the other side. I have dq times R1C equals C times epsilon minus Q times dt. All right. So now keep in mind I have a dq over here. So I have I need to integrate an expression that has Q in it. So here I have CE, I'm just going to call it E for the sake of simplicity. So CE minus Q on the right-hand side, I need to move that over here. And then this R1C, I'm going to move this over to the DT side. So I'm going to do it up here on the top right-hand corner. I have DQ over CE minus Q is equal to DT over R1C. And then we get to integrate. So something I'm going to do before I integrate, and at the end of the day, it doesn't matter. These are just some steps to help simplify the process. You could integrate this straight up, but you're going to want to be careful because if you notice that this q has a minus sign in front, it's CE minus q. So if you were to integrate, say, a function in the form of, in class, I believe we did 1 over x plus a, where a is some constant. All right, that's going to be ln of x plus a. But if you integrate 1 over a minus x, well, that's different. That's going to be negative ln of a minus x. All right, so in other words, the integral of negative 1 over x is actually negative ln x. Okay, so yeah, you just want to be careful about that. Anyways, let's, what I'm going to do is I'm just going to change the denominator so that q is positive. Okay, so I'm going to have dq over q minus ce is equal to negative dt over r1c. All right, and again, technically it doesn't matter if you do the simplifying step now. It's just that once you start dealing with the natural logs, and if you're worrying about whether or not the variable you're integrating is positive or negative, it's just you're much more likely to make a mistake, especially if you put in the bounds of integration. So let's do this first step to make it a little bit easier. And I'm going to integrate both sides of the equation. And for the left-hand expression, I'm going to integrate from when the charge in the capacitor starts at 0 to when the charge is at some later time, q sub t. All right, so q is a function of time. That's what we're trying to get. For the right-hand side, I'm going to integrate from t equals 0 to some later time t. Okay, so when we perform the integrals, what we end up with is ln, so natural log of q minus c times e. Let's see, so yeah, c times, q minus c times e, minus ln of negative e times c. All right. Oh, whoops, can I turn off the autocorrect? I guess not. And then that's going to equal negative t over r1c. All right, so now at this point, what we need to do is we need to combine these two expressions. So a property of logs, if you're adding or subtracting logs, you can either, if you're adding logs, you just multiply the arguments, or if you're subtracting logs, you take the ratio of the arguments. So here I have ln of q minus c e all over, I have CE and EC. I'm just going to put EC. Let's see here. Okay. EC. Okay, so I have Q minus E times C all over negative EC. That equals negative T over R1C. Okay. And so let's evaluate this. We have Q minus E times C over negative E times C is equal to E raised to negative T over R1C. Okay. So now, almost done. I should say that this is Q sub T. This Q is a function of time. I'm running out of space here. But yeah, this is Q as a function of time, because that's what we're trying to find. It's the same difference. So now let's basically rewrite this fraction here. All right, where am I going to find some space? All right, so I'm going to rewrite this fraction I have here. So let's see, I end up with this is basically 1 minus Q as a function of time over epsilon C. All right, so I'm rewriting this fraction, Q minus epsilon times C over negative epsilon times C, as this, 1 minus Q sub T over epsilon C. And that has to equal e to negative T over R1C. All right, almost done. I'm going to rearrange this expression one more time. And I have Q as a function of time over epsilon, that's the EMF of the battery, times C, the capacitance of the capacitor, is equal to 1 minus e to negative T over R1C. And then finally, we have our expression. So Q is a function of time is equal to epsilon times C times 1 minus e to negative T over R1C. And that should match the expression you have in your notes. And I know it's a bit of a process, but we should know how to do it. We should learn how to do it. And if you struggle with this, obviously you can ask me for help. But again, keep in mind, this part, like part 2 of part A on the scoring guidelines, this kind of question where they ask you to solve for the differential equation, that's only ever worth like about 2 points on one FRQ for the AP exam. So it's not the end of the world if you trip up on your derivation, but you should practice it and try to get it right, because you might as well learn how to do it. So that's how you solve to find the equation of the charge of the capacitor as a function of time. So now let's move on. For part 3, after switch 1 has been closed for a long time, it's opened again. Switch 2 is then closed. For times after switch 2 is closed, indicate whether the magnitude of the current in the resistor of resistance R2 increases, decreases, or remains the same. Justify your answer using physics principles without manipulating or deriving equations. So the idea here is that we're going to charge up the capacitor. We're going to turn off switch 1. That's going to disconnect us from the battery. R1 is no longer making a complete circuit with the battery, and it's not connected to the capacitor. At least it doesn't make a complete circuit with the capacitor, so R1's not going to matter. I then close switch 2, and the fully charged capacitor is going to start dissipating its charge into resistor R2. And because this can seem a bit abstract, because it is, I actually have some circuits that I built on the circuit simulator, and I highly recommend you do this for any of your problems. If you're struggling to understand how the electricity flows within the circuit, well, you can just simulate it to understand how it's working. So first, what we're going to do is I'm going to disconnect both switches. I'm going to start with part A of the problem, where we charged up our capacitor. So as you can see here, we have a nicely charged capacitor. I'm going to disconnect the battery, and my capacitor remains charged. And we're going to see how the current going through the resistor is going to change. All right. Now I'm purely showing this so you can understand the explanation. So I'm going to close this switch, and we're going to let's first predict. I know that the voltage across the resistor is going to equal the voltage across the capacitor. And so the capacitor is going to start to discharge into the resistor. And as the capacitor discharges, the voltage should drop. And if the voltage drops across the resistor, then the current going through the resistor will decrease as a function of time. So let's just see it. I'm going to close the switch now. And we see here that the current clearly decreases until the capacitor is fully discharged. All right. So that's the answer to that problem. Now, you can't necessarily say, I ran it in a simulator. So we have to justify our answer using physics principles. As I said, basically, we know that the capacitor is connected to resistor R2, and it's going to be decreasing for times after switch 2 is closed, and the potential difference across the resistor is equal to that of the capacitor. Charge leaves the capacitor as current goes through the resistor, and that decreases the voltage across the capacitor, which in turn decreases the voltage across the resistor, and that decreases the current through the resistor. So that's a very long line of reasoning, but that's basically how you solve this problem. Just to see it again in the simulator, let's charge up our capacitor again. Okay, so now our capacitor is charged. And, well, let's wait for the current to finish charging it. So now our capacitor is fully charged. I'm now going to discharge the capacitor through the resistor. And as the capacitor is discharging, we see that the current through the resistor is going to be decreasing until it reaches 0, which indicates that the capacitor is fully discharged. So hopefully you're able to follow along with that. I think the simulation really helps in our understanding of the problem. So is that pretty much it? Okay, so now the capacitor is replaced with a battery with an EMF of epsilon over 5. The two resistors of the same resistance R1 are used. Both switches are closed. The figure also shows point P located just above the battery with EMF epsilon over 5. Derive an expression for the current at point P and express your answer in terms of epsilon, R1, and physical constants as appropriate. All right, so now we replace the capacitor with a battery, and we need to use Kirchhoff's loop rule in order to figure out what the current is at point P. So what I'm going to do is I'm going to use two different colors to show my two loops. So here's my first loop. All right, and let's see how the potential changes as I go through my loop on the left-hand side. So here I see that the potential increases by the EMF of the battery on the left, and then it's going to drop. I'm going to call this I1, R1. All right, so this loop is I1. All right, and we know that it's also going to actually decrease across the other battery. And the reason why is as we draw our loop, so here we're going from negative terminal of the battery to the positive terminal. That's on the left-hand side. So the electric potential increases, the voltage increases. Then the voltage is going to drop as it goes across resistor R1, all right, and that's the voltage drop of the resistor. But the voltage is also going to drop because it's going from the positive terminal of the battery to the negative terminal of the battery, and it's going to drop by epsilon over 5. So that's our equation for our left-hand loop. If we want to solve for the current I1 going through point P, so keep in mind there's going to be two contributions to the current. There's going to be current from the left-hand loop, there's going to be current from the right-hand loop. So from the left-hand loop, I should say, I know the sum of the voltage drops have to equal 0. That's Kirchhoff's loop rule. And let's solve for I1. So now I have I1 R1 has to equal 4 over 5 epsilon. Okay, and that means that I1 is equal to, well, 4 over 5 epsilon divided by R1. So now let's do the right-hand loop. I'm going to do this in blue. So I'm also going to draw a loop going clockwise. And I'll just start from the negative terminal of the battery just because it's a habit. And here I have now that since I'm starting from the negative terminal of the battery over here on the right-hand loop, the electric potential is going to increase. So it's going to have a positive epsilon over 5. Okay, and then the potential is going to drop, right? So now the current is going down through the resistor, and it's going to drop by I2 times R1. So I'm going to label this current on the right-hand loop as I2. And then the current going through point P is going to be a combination of these two currents, right? So let's first solve for I2. So if the sum of the voltage drops has to equal 0, then I2 is equal to epsilon over 5 divided by R1. So epsilon over 5 R1. All right. So now let's look at what's going on for our current through point P. So through point P, I have a contribution of current from the right-hand loop going up. That's equal to epsilon over 5 R1. And then I have a contribution of the current from the left-hand loop going down with a magnitude of 4 over 5 epsilon over R1. All right, so if I combine these two fractions together, I have a current going down into the battery, into the positive terminal of the battery of 4 over 5 epsilon over R1. And then I have a current from the right-hand loop coming out of the battery equal to epsilon over 5R1. And if I combine those two currents, I'm going to call current coming out of the battery as positive. It doesn't really, it just says what's the current through point P. For the current at point P, not specifying a particular direction. All right, so just the magnitude of the current. So I'll just take the larger current minus the smaller one. So I have 4 over 5 epsilon over R1 minus 1 over 5 epsilon over R1. And that's how we get our answer of 3 over 5 epsilon over R1. All right, so that's our answer. Now let's simulate it. So again, I think it's so much easier to understand circuits if we can visually see what's going on. So here I built a circuit for part C, and I am using actual values here. So I have a 10 volts for the EMF of the left-hand battery, and then the battery in the middle is going to have a voltage of 2 volts, all right, because that's E over 5. And then I put these two 10 ohm resistors to represent R1. So here, let's make sure all right, so now we're going to see the current from both loops. So now here's the current from the left-hand loop. If I turn this on, I get a current going through the battery of 0.8 amps, right? So you can imagine point P is, point P, the current through point P is going to be the same as the current through the battery because they're, in the same wire. But I have 0.8 amps going down into the battery from the left-hand loop. From the right-hand loop, I have a current of 0.2 amps coming out of the battery. All right, so if I have 0.2 amps coming out of the battery from Kirchhoff's loop rule on the right-hand loop, and I have 0.8 going into the battery, right? That's like our EMF over, or times 4 over 5, right? So that's the green loop here from the problem, right? So I have 4 over 5 epsilon over R1 going into the battery, and I have epsilon over 5 R1 going out of the battery. All right, and then if I combine those two together, I end up with 0.6 amps going into the battery. So to make that more visually clear, I'm going to remove some of the clutter. Let's do that one more time. So on the left-hand loop, I have 0.8 amps going into the battery. Okay, on the right-hand loop, I have 0.2 amps coming out of the battery. And then when I combine both, I now have 0.6 amps going into the battery. So that's how you do the first one. Now, moving on to the second one. All right, here's FRQ number 2. Let's see here. All right. So now I have this circuit with all these resistors. And what we need to do is we need to draw dots to represent the electric potential at each labeled location except location E, which is already plotted. So basically we're tracking the electric potential as we go through the circuit. All right. So let's get the easy ones out of the way, and then we'll have to reason about all the other ones. So here I know that for, oh goodness, what happened? All right, there we go. All right. So here at, come on, you gotta be kidding me. All right, maybe I got to draw something on it for it to not close. All right, so for here at point F, I know that's directly connected to the positive terminal of the battery. There's no circuit element that's going to have a potential drop across of it. So here the voltage or the electric potential is just the EMF of the battery. At point A, it's the same. Through the switch, doesn't change. Point B, still the EMF of the battery. And then finally, we hit a resistor, which we know there's going to be a voltage drop across that resistor. So now we need to figure out what the EMF is at point C. Well, in order to do this, you kind of need to know the total load on the battery. So it says here that all these resistors are the same. They have the same resistance R naught. So I'm going to simplify the circuit and redraw. I'm going to do it one step at a time. So I have my battery here, all these wires. Then I have R naught. And then these two resistors are in parallel, right? So these two resistors are in parallel. If you remember that resistors in parallel, their equivalent resistance is 1 over the sum of the reciprocals, right? And so both of these have a value of R naught. So that's 2 over R naught. And then don't forget to flip it at the end. So my equivalent resistance is R naught over 2. All right, so I have a resistor of R naught over 2 over here, right? So this is like R naught over 2. And then this resistor is still R naught. So these are now all in series. And for series, you just add them up. So the load on the battery is basically a resistor with a value of 2.5 times R naught. Or I can just write that as 5 over 2. So 5 over 2 R naught. So then that means the current going through the battery, through this circuit, is going to be, we know that voltage is equal to current times resistance. So my voltage is the EMF of the battery. My resistance is 5/2 R naught. So my I is equal to 2 over 5 times V over R naught. Or I should say epsilon over R naught. So now I know that my current is 2 over 5 epsilon over R naught, and it's going it's going through a resistor of value R naught. Then the potential at this point here, so my delta V for this resistor of R naught is equal to the current, which is 2/5 epsilon over R naught, times the value of the resistance, which is R naught. And so I just get 2/5 epsilon. I keep putting epsilon naught. It's just epsilon for the EMF of the battery. So 2/5 epsilon. Now that's not the actual value. That is how much the electric potential changes, right? So I started with the EMF of the battery, and it drops across the resistor by an amount equal to 2/5 epsilon. So the amount that's remaining here is 3/5 epsilon. So at point C, it's 3/5 epsilon. Okay, I hope that makes sense. So the delta V across this resistor has to be 2/5 epsilon. So then if I drop 2/5 epsilon from epsilon, I end up with a potential of 3/5 epsilon. And then here, the drop across these two resistors that are in parallel, well, they have an equivalent resistance of R naught over 2, right? So then the delta V over here is going to be 2/5 times the EMF of the battery over R naught times R naught over 2. And that's just 1/5 of epsilon. So now it's going to drop 1/5 epsilon. So it goes from 3/5 epsilon to 2/5 epsilon. And that's the value of the potential at point D. It's then going to drop another 2/5 epsilon to reach 0 volts, which is the potential of the negative terminal of the battery. All right, so let's label all these points. So we say that point A is at epsilon. So point A is at epsilon. Oh, wait, whoops, that's not point A. This is point A. Point A is at epsilon. Point B is at epsilon. Point C is at 3/5 epsilon. So 1, 2, 3. All right, so that's point C, 3/5 epsilon. Point D is going to be at 2/5 epsilon. And point F is going to be at epsilon, because we know that point E is directly connected to the negative terminal of the battery. And that's pretty much it for that one. So now I also have a example. So that seems, again, this is all kind of abstract when you're dealing with pure variables. Let's use some numbers. So I built another circuit, and that's this problem here. So what we're going to do is I'm going to turn this circuit on. We're going to have electricity flowing through the circuit, and I'm going to measure the voltage with respect to the negative terminal of the battery. So I have my black probe of my multimeter on the negative terminal, that's 0 volts. I can see here I have a nice 10-volt battery. So the voltage reading of my voltmeter is, well, 10 volts. And then this is going to be, let's see, what is it? What does it go? It goes, A, B, C, D, E, F. All right, got it. Whoops. Let's see here. Nope, that's not it. All right, over here. So here I have, all right, here's point A. Point A is at 10 volts. Point B, 10 volts, 10 volts, 10 volts, all the way up until I reach the first resistor. So all this wire on the left of the battery, before it hits a resistor, this entire thing's at 10 volts. Then it drops when it goes across the resistor. All right, so we said it's going to drop by a value of 2/5 epsilon naught, or 2/5 epsilon. which is 2/5 the EMF of the battery, which for this numerical example, it's 10 volts. So I say it's going to drop 4 volts. So it's got to go from 10 volts to 6 volts, because that's a voltage drop of 4 volts, and go figure. There it is, 6 volts. All right. So this is a very useful tool, this circuit construction kit. I think if you're struggling with any of the problems while you're studying, you just build it. Build the circuit, see what happens, and that's going to help you build the intuition. Because if you understand the basic principles behind circuits, the problems actually aren't all that tricky. It's just testing the fundamentals. So here we go 6 volts, and then here these two resistors in parallel. The voltage is going to drop by 1/5 the EMF of the battery. So I'm going to say it's going to drop another 2 volts, and it's going to go down to 4 volts. And there you go. And then finally, it's going to drop another 4 volts, going back down to 0. All right. So this, I hope that these circuits, by actually building the circuits and seeing what the actual values are, hopefully this makes more sense. So now back to the problem. So right now, let's derive an expression. Okay. So let's derive an expression for the total rate at which energy is dissipated by the resistors of the circuit. Express your answers in terms of epsilon, R naught, and physical constants as appropriate. Well, I know that the rate of energy dissipation, that's just power, and the power of a circuit is current times voltage. Two other ways to write this is I squared R or V squared over R. And this just comes from Ohm's law. So V equals IR. I can do some substitution to write it out in these different formats. So we know that we can just use V squared over R for the power that's being dissipated by the circuit. I already solved for the equivalent resistance up there. So I know that the equivalent resistance is equal to, what did it come out to? Yeah. So 5/2 R naught. So 5/2 R naught. Okay. And I know that the voltage is going to be the EMF of the battery. So then the power dissipation through the battery is the EMF squared divided by 5/2 R naught. And let's simplify this fraction. You get 2 times EMF squared over 5 R naught. That is the power dissipated by the circuit. So now part C, we're going to replace the resistor here with a capacitor. And on the axes, we got to sketch a graph that as follows. Draw a line to curve represent the voltage across the capacitor as a function of t. All right, so now with this graph, we know it's going to be a decaying exponential. And the reason why it says here is replace the capacitor, the switch is closed, circuit's allowed to reach steady state. So when the circuit's closed, the capacitor is going to start to charge up. So initially, the capacitor that acts like a wire. There's no voltage across it. All the current's going to start to flow into the capacitor, and then it's going to be split between the capacitor and the resistor until the capacitor is fully charged, and no more current is going to flow into the capacitor. It's going to all go through the resistor. One thing that you should see immediately is that these two circuit elements, the capacitor and resistor R3, they're in parallel with each other. So because they're in parallel with each other, they have to have the same potential difference. All right. So parallel, same voltage. Memorize that. If they're in series, it's same current, but in parallel, same voltage. So we know this capacitor is going to charge up, and then we have to graph the voltage across the capacitor once the switch is opened. So as soon as we open the switch, it's going to be disconnected from the battery, and we need to see how what the voltage is across the capacitor. So we know it's going to be a decaying exponential immediately before t equals 0, and express the potential difference in terms of epsilon naught and physical constants as appropriate. So now we got to see, well, what's this voltage across the battery right before? So this is after we've charged the battery, it's reached steady state. I'm sorry, not the battery, what am I saying? After we charge the capacitor, it reaches steady state, and then we're going to close the switch that connects it to, all right. We're going to open the switch at time t equals 0. So the capacitor discharges into resistor R3. And here we know it's going to be a decaying exponential, okay? And it's going to asymptotically approach 0. But now what's this value for the voltage across the capacitor? Well, I know that once the capacitor is fully charged, it has to have the same potential difference as the resistor R3, okay? So here I have 3 resistors that all have the same value for the resistance. So when the capacitor is fully charged, there's not going to be any more current flowing into the capacitor. There's going to be current flowing through resistor R3 and R1 and R4, right? So when the capacitor reaches steady state, there's not going to be any more current flowing into it. All the current's going to flow through these 3 resistors. And that means that the equivalent resistance of that circuit is 3R0, right? Because these 3 resistors, R1, R3, and R4, they're all in series with the battery. Once the capacitor is fully charged, there's not going to be any more current flowing into the capacitor. All right, so that's how we know the equivalent resistance of the circuit becomes 3R0. Therefore, the potential drop from here to here, all right, so we got to think the potential for the whole circuit is the EMF of the battery. If I have 3 equal resistors and the potential drops across each resistor, then the potential at this point is going to end up being epsilon. The potential at this point is going to be epsilon, or 2 epsilon over 3. The potential at this point is going to be epsilon over 3. And then finally, the potential here is going to be 0. That's the negative terminal of the battery. So the drop across resistor R3, the delta V, is equal to epsilon over 3. And that is going to be what we put over here. So this point here is epsilon over 3. Now let's test it. All right. First, what I'm going to do is I'm going to read part D so we can test both C and D on the circuit simulator. So for part D, it says that they replace R3 with a different resistor that has a greater resistance. R new is greater than R0, and the circuit's allowed to reach steady state with the switch closed. And then with the graph of the capacitor's potential difference, how would it change? Describe some feature that would be different from the graph we drew in part C. Justify your answer. Alrighty, so now it's circuit time. So here, that's a different circuit. Okay, I didn't build this one because, yeah, I remember now. It's going to be an easy fix. It's because I didn't want to build this one took the most time to build. So I'm just going to simply switch this out for a capacitor. No problem. All right, let's connect all this up. That's connected there, and you can see the capacitor is already charging up. Okay, so here the circuit has now reached a steady state, and we need to measure the voltage across the capacitor. So how do we know that it's epsilon over 3? Well, because we understand the principles of circuits. But in terms of like actually solving for it, all right, let's use real values. So I know that the EMF of the battery is 10 volts, all right? And notice there's no current flowing through the capacitor, right? So let me reset the charge in the capacitor. We see that initially there's some current flowing through it as it's charging up, but as soon as it's fully charged, it's as if the capacitor isn't there anymore. There's no current flowing through it. It's reached its full charge given the potential difference with the resistor on the right. So the capacitor has a potential difference of 3.33 volts. That's the same potential difference as this resistor here because those two circuit elements are in parallel, right? It's going to end up being 1/3 of the voltage of the battery because I have basically 3 resistors in series, right? So here I see the voltage is 10 volts, and then it's going to drop by 3.33, right? It's going to go to 6.67. Then it's going to drop again from 6.67 to 3.33. And then it's going to drop again to 0. All right, so we see that the voltage drops as it goes across each resistor. As current flows through each resistor, the voltage has to drop. All right, and since they're all equal resistance, I have 3 resistors in series, the voltage drop is going to be the same amongst all 3, and the total has to be the voltage drop across the battery. All right, so again, I hope these examples help us understand what's going on. But this also shows that the potential difference between the capacitor and the resistor on the right has to be the same. Those two are in parallel. They have to have the same potential difference. All right, so then, and now to answer part D, we're going to increase the resistance of the resistor on the right. I need to double check to make sure. It reached steady state, and then describe how some features. All right, so now we're using a new resistor that has a greater resistance. Okay, so we see here that the potential across the capacitor is 3.33. And if I increase this resistor, let's see what happens to the potential across the capacitor. And we see here the potential across the capacitor is increasing, right? And if you think about it, this actually makes sense. So as the resistor on the right-hand side gets larger and larger, right, the voltage drop across it equal to I times R. These three resistors have to have the same current, right, because they're all in series. Well, once the circuit reaches steady state. They don't while the capacitor is charging. But once it reaches steady state, we see that there's no more current flowing into the capacitor. The three resistors here are all in series. And this resistor on the right, as the resistance increases, it has to have a larger voltage drop than the other two resistors. So with these numbers, I have a voltage drop of 8.57. Okay, and then the voltage drop across these resistors is going to be, well, 1/14 of the voltage. Well, actually, yeah, it's 1/14, right? Because it's the equivalent resistance is 140, and yeah, okay. So, anyways, here I have 0.71 volts across this resistor, 0.71 volts across this resistor. I guess I should put it like this, right? Because this is at higher voltage, and then across this resistor, I have 8.57 volts. So going back to answering part D, right, it's asking about the potential difference as a function of time. What are some features that would be different than in the graph that you drew? Well, for one, I know that the potential difference is going to be larger, right? So the potential difference across the capacitor is going to be larger because it has to have the same potential difference as the resistor. And if I put in a new resistor that's larger, as we saw in the simulation, it has to have a larger voltage drop across it, given that it has to have the same current as the battery and as the other two resistors. And we know the voltage drop across the resistor is I times R. All right, so if it has a larger resistance, there's going to be a larger voltage drop. And that has to be the same voltage drop as a capacitor because they're in parallel. The new resistor and the capacitor are in parallel with each other. So the voltage drop across the capacitor is going to increase. And that's enough to answer that question because it's just described. You have to justify just one difference, right? So it says you have to describe how some feature of the graph would change. You only need to describe and justify one feature. Another feature that would change would be the amount of time it takes to discharge the capacitor. Or actually, hold on. It says here, replace a different resistor, reach steady state. All right, the switch is then open at time t equals 0. So not only is the voltage across the capacitor going to be greater, it's also going to take longer for that capacitor to discharge because there's a greater resistor that is connected to the capacitor. So since the resistor is going to be greater, then the current flowing through the resistor at a given potential difference is also going to be smaller, right? It has a greater resistance. So it's going to take longer, right? So I know the time constant, this is baked from the equation that we saw in class, the voltage across the capacitor, right? That has the, it's going to be equal to the voltage, well, in that case, it was voltage of the battery, but you know what I mean? It's going to have that 1 minus e to negative t over RC factor in the equation as the capacitor is discharging. So if I have a larger resistor, well, in this equation, e to the negative t over RC, okay, well, then as t approaches infinity, right? It's going to take longer for the capacitor to fully discharge, since the denominator is going to get larger if you have a larger resistor. So there are two different things that would change with the graph, and you only actually have to mention one to get the points for that problem. Going back to the simulator, all right, we can actually simulate this. So here, let's, I guess, measure how long it takes for the capacitor to discharge. All right. So with the 120 ohms, I might have regretted doing this. It shouldn't take that long. It's only 0.1 farad. Actually, it feels, yeah, it shouldn't take that long. All right, I'm going to stop it at 30 seconds. If it takes longer than 30 seconds. We know it takes longer than 30 seconds. All right, it takes longer than 30 seconds. So now let's charge it up again. I'm going to switch this to 10 ohms to make it like the original example. 10 ohms. Okay, so let's charge this back up. It reaches steady state. So right now we're at steady state. And let's reset our stopwatch and let's see how long it takes to fully discharge. Much less time. Right, so it's going to take well over 30 seconds when we had a larger resistor. And now with the original resistor, it only took like 10 seconds to fully discharge that capacitor. So anyways, moving on. So now we're going to move on to problem number 3. So here we have an experiment. We have to determine a non-ideal battery's internal resistance R sub I, and the students have various different resistors of different resistances, all unknown, as well as wires, voltmeters, ammeters that can all be considered ideal. So what data can we collect to determine the resistor Ri, that's the internal resistance of the battery, by making a linear graph and include the measurements made along with the corresponding equipment needed for each measurement and provide enough detail. So actually, let's just use the circuit analysis again. So at this point, I am going to remove that circuit. Do I have real batteries here? No, I do not have real batteries. Wait, there isn't an advanced? Oh, now I kind of regret doing this. Circuit construction kit AC. What if I do lab? Do I get real batteries? I sure don't. Well, that's awkward. Now I'm committed. Circuit construction kit. DC, virtual lab. Okay. This one had it. I saw it. Yes, the advanced features. Okay, so now we're going to have, that 10 ohm internal resistance. That's pretty bad. All right, so here now I have a real battery. Wait. Is there... Okay, let's test this. So 9 volts, if I put a resistor across this battery. Okay. Wait, is there a real light bulb? Oh, okay, there we go. All right, good. So if I add a resistor here, look at what happens. If I have a real battery, look at what happens to the terminal voltage across the battery. So here I'm going to get a voltmeter. This is a 9-volt battery, but because the battery has some internal resistance, the terminal voltage is not 9 volts. And that's basically how all batteries work. It depends on the chemistry, and it depends on the load on the battery, but it behaves as if the battery has some resistance inside, which it does. Some batteries have more than others, like a AA battery. It's got quite a bit of internal resistance, especially, the voltage really sags if you put a large load across it. But then other batteries, like very high quality lithium ion batteries from Samsung, those have very, very, very low terminal resistance, and they can carry a lot of current. So this is basically has to do with the physical properties of the batteries and the fact that the batteries are going to be heating up as the chemical reaction goes on, and basically everything has a resistance. For simplification purposes, we assume that wires don't have a resistance or batteries don't have a resistance, but in actuality they do. So wires have a resistance because they have resistivity, and batteries have a resistance for the same reasons and many more due to the chemistry of the battery. So here we can clearly see that the voltage across the battery, the terminal voltage, is not equal to the rated voltage of the battery. And that happens when I have some current flowing through the battery. It acts as if there's a tiny resistor inside, and there's a voltage drop across the terminals. If I disconnect the circuit, I measure 9 volts. And then if I increase the... Actually, I think I have to decrease... If I decrease the resistance of this resistor, yep. If I decrease the resistance, I'm increasing the current. And if I increase the current, then that means that... Well, actually, hold on just a second. Oh, I'm actually... That's awkward. The voltage across the battery is decreasing because I was decreasing the voltage. Okay, so now let's change the resistance. So as I change the resistance of the resistor, we see the current increases, therefore the terminal voltage across the battery decreases, right? And you can think about it as like, based on the load on the battery. So if you short out a battery, if I just connect a wire from positive and negative, don't do that, especially not with a lithium ion battery. But if you were to do that with a AA battery, the terminal voltage would really get low, and the battery would just heat up. It would not catch on fire, but it would if it was a lithium ion battery. Actually, let's see what happens. Yeah. Does it not? Oh, okay. There we go. There, I remember this. Okay, so if you do it within the circuit simulator, it even simulates a battery fire. Look at that current. Crazy. So anyways, let's get to the problem. Oh, wait, now everything's on fire. All right, I got to reset. So here, the reason I'm doing this is because I really want us to kind of understand what the internal resistance of a battery is, right? And also like how this experiment's going to work. So basically what you're going to do with this experiment is you have different resistors, and you're going to take a voltmeter. You're going to measure the voltage across the battery. You're going to record it, and you're going to measure the current going through the battery. So if I know the current going through the battery, and I know the voltage across the battery, and I know the resistance of the resistor I attached to the battery, then I can effectively calculate the resistance of the battery, because the resistance of the battery is in series. The internal resistance of the battery is in series with the resistor that it's connected to, right? And then you're going to record all those measurements. You're then going to repeat for different resistance values, right? So say you do it with a 10 ohm resistor and a 24 ohm resistor, 37 ohm resistor. Notice how the voltage across the battery is changing. And if you want to determine what that resistance, that internal resistance of the battery, you take the terminal voltage of the battery, and the current from the battery, and you can calculate what its internal resistance is. Well, it's going to give you the resistance of the entire load of the circuit. So then if you subtract out the resistor it's connected to, right? Let's make it a little bit more obvious. I have an internal resistance of about 1. So if I make the internal resistance... All right, so when this battery with an internal resistance of 1 is connected to a resistor with a value of 1 ohm, okay, the total resistance of the circuit is actually 2 ohms, right? So then the current through the circuit from this 9-volt battery is going to be 4.5 ohms. And so, yeah, you can just take the terminal voltage of the battery divided by the current through the battery, and that tells you the internal resistance of the battery. So I know this battery has an internal resistance of 1 ohm, right? And you can do that for, let's say it was 3 ohms. And then it should be 7.5. All right, wait, hold on a second. 6.75, 2.25. Do you still get, let's see here. So in this case, the total resistance of the circuit is 4 ohms. The terminal voltage of the battery is 6.75 volts. And the current is 2.25 amps going through the battery. So that would mean the voltage drop across the resistor is 6.75 volts. And the current through the resistor is 2.25, which makes sense. That's going to be 3 ohms. But the battery is rated at 9 volts. So, okay, there we go. That's how you would find it for a battery. You would take the rating of the battery. We know that the battery under no load is 9 volts. So the voltage at the terminals is decreasing by 2.25. And if I have 2.25 amps of current flowing through the battery, and it has a terminal voltage that decreases by 2.25, the internal resistance of this battery is 1 ohm. There you go. That's the reasoning you want to have. By the way, you don't have to explain any of that in the problem. I just felt like doing it to help us understand the concept of internal resistance, right? You just have to describe what data you would collect. So to go through this problem, connect an ammeter and a resistor in series with the battery and a voltmeter in parallel with the battery. Record the current and voltage of the battery and repeat for multiple resistors or resistor combination, right? So you're going to get a range of data with different values of different resistors connected to the battery. And then from that data, you can then determine the internal resistance as we talked about, right? So you know the rating of the voltage of the battery based on the different resistors that are connected to it. The terminal voltage across the battery is going to change, and that difference in the rated voltage, right? So that is to say the terminal voltage when there's no load across the battery, and then how much the voltage drops at the terminal. So as soon as you connect the load to the battery, the voltage at the terminals is going to decrease, and then that's how you determine the internal resistance. You look at how much the voltage drops through the battery, and then you divide that by the current through the battery, and that tells you the resistance, the internal resistance of the battery. All right, for part B, now they collect some data. They want to create a linear graph that could determine the internal resistance of the battery. Okay, so going through the same procedure that we just talked about. So we know the potential difference across the battery here. So we have that the terminal voltage, whoops, I got to edit this. Let's see here, markup. So here I have my battery. I'm actually going to draw a little AA battery so we can visualize it. Positive terminal battery, negative terminal battery. And it's as if there's a little internal resistor inside of the battery. All right, and that's going to be connected to some load. Okay, whatever resistor you're gathering data on, or whatever sets of resistors you're gathering data on. And if I measure the current going through the battery, so if I connect an ammeter, so here's an ammeter in series with the battery, and then I connect a voltmeter in parallel to the battery, okay, I'm going to know the voltage across the battery, and I know the current going through the battery. All right, so the EMF, that's the electromotive force. That's basically the rating of the battery. So if you measure the voltage at the terminals when there's no load across the battery, there's no current going through it, that's the electromotive force of the battery. That's its rated voltage. And then as I connect the load across a real battery, the terminal voltage will decrease. And that's how you figure out the internal resistance. So I know that the EMF of the battery is equal to the voltage at the terminals plus the current going through the resistor, right? Yeah. So there's a voltage drop across the load of the battery, and then there's the terminal voltage of the battery itself. Actually, I'm mixing this up a bit. So we want to use specifically the battery. Hold on a second. I'm going to rewrite this. So as current goes through the battery, the terminal voltage decreases. So the terminal voltage, which is what we measure with our voltmeter, is equal to the EMF of the battery minus the current going through the battery, all right, times the internal resistance of the battery. All right, there we go. That's how we want to write it. Yeah, because then it just gets awkward if you're using the actual load of the battery itself. So what you want to do is, if you record the current, so this is how you want to design the experiment. So we're not even going to necessarily care about the potential difference. We're here to determine what the internal resistance of the battery is. So we know the current going through the battery, the EMF of the battery, and the terminal voltage of the battery with the voltmeter. They're then going to plot that data for various values. So the different resistances, the different loads across the battery are basically changing what the current through the battery is. So the current is going to be our independent variable, and the terminal voltage is going to be the dependent variable. So the terminal voltage depends on the load that's put across the battery. And then you're going to make a graph of the voltage, the terminal voltage of the battery with respect to the current going through the battery. In other words, the voltmeter reading with respect to the ammeter reading, and the slope is going to be is going to give you the internal resistance of the battery. So let's linearize this, right? So here my dependent is going to be my voltage, right? So that's my dependent variable. I'm going to graph that on the y, on the vertical axis, and my independent variable is going to be the current, so it's going to be the current that's going through the load, right? So when you hook the battery up to a resistor, that's going to be our independent variable. And then if I look at the slope of this graph, right, so I'm going to rewrite this as V terminal is equal to negative I times the internal resistance. Actually, I should write it like this. So negative R internal times I plus the EMF of the battery. And then we're going to linearize this. So y is equal to mx plus b. And then the slope, let's use a different color. So this slope here is going to give me the internal resistance of the battery. All right, and that's how you would design that experiment. Just to clarify again with the simulation, right? So here, what we would be doing is we would take these readings from the voltmeter, right? So here, say this is the first resistor you set up in your experiment. All right, we have a resistor of 3 ohms, and we see that the voltage at the terminal of the battery is 6.75 volts, and the current going through it is 2.25 amps. And as I change the resistance, so now I put a 4 ohm resistor, these are the values I get, plot it. I put a 5 ohm resistor, those are the values I get, plot it. And then when you plot all these values, okay, and then you take the slope, that's going to give you the internal resistance of the battery. All right. So now we have to do a resistivity experiment. So this one's a little tedious because they tell you the diameters of the wires, but it's really not too bad. They don't tell you the area. And also this one's a bit of a mix-up. So the experiment that we did in class, as a classic example, we took wires of the same gauge, of the same material, and we took different lengths of wire to see how the resistance changes. In this experiment, what they're doing is they're going to determine the resistivity, but they're going to have different voltage and current values, and they're all the same length, but they have different diameters. So it's just a different way of doing the same kind of lab. Instead of having varying lengths, which change the resistances of the wires, we have varying gauges, varying diameters that change the resistance of the wire. So for this one, to even get started about thinking how to design the experiment, we need to remember the equation for resistivity and resistance. So the resistance for a wire is equal to its resistivity times the length of the wire divided by the area. Now, if we have a wire, so let's look at a cross-section of a wire. Well, that wire has a certain radius, right? And the area of that wire is pi r squared. But I know that the radius is equal to 1/2 of the diameter, right? So if I write this in terms of the diameter, I know that the area is pi over 4 times the diameter squared. I'll use capital D because that's what they use in the table. Times the diameter squared. All right. I know the length's going to stay the same. That's constant. It has to be 10 meters. The resistivity is going to be the same because it's all the same material. They're made of the same material. And the only thing that's going to be different is the resistances, right? And the way we're going to get the resistances is not by measuring it directly with an ohm meter. We're going to use an ammeter and a voltmeter to determine what the resistances are. In terms of determining the resistivity, let's think about our axes. So here, what I'm going to want to put is our independent variable is the diameter of our wires, right? So I'm going to rewrite A in terms of D. So I have R is equal to rho times L over pi over 4 times D squared. Okay? And basically I'm going to do multiple steps at the same time. I always like looking at the equation first to kind of figure out just getting it all done in one step. So here, what we want to do is we need to rewrite this expression. So I'm going to put all the constants to be encoded into the slope, and then my independent and dependent variables. In this case, my independent has to be the diameter. So on the horizontal axis, I'm going to put, actually, see, this is why I want to write the equation first. So we're not going to do diameter. We're going to do 1 over the, it's going to be 1 over diameter squared. You're going to see why in a second. So let's see here. We know that we have R is equal to rho times L over pi over 4, okay, times 1 over D squared. Okay, so here, let's just rewrite this as 4 times L. It's messy. So 4 times rho times L over pi. And then my resistance R, they don't tell us, but we have to calculate it. So I know that if V is equal to I times R, R is equal to V over I. All right, that's the basic idea. And that's what you're going to be putting it in the tables in terms of your calculated values. And on the vertical axis, so I have Y is equal to M X plus B. And then we're going to do our linearization. So on the vertical axis, I'm going to put R. On the horizontal axis, I'm going to put 1 over D squared. And my slope is going to be 4 rho times L over pi. Okay. Now this R here, that's going to be calculated from your delta V and your I, right? So V over I. So I could have, say, R here, which is equal to delta V over I. That's going to be measured in ohms. And then here I have 1 over d squared. Okay, and that's going to be measured in, you do 1 over meter squared for that one. So it's going to be in terms of 1 over meter squared. So yeah, that's pretty much it. On the horizontal axis, I'm going to put 1 over d squared. That's our independent variable. And our resistance depends on our diameter of our wire. So thicker wire, less resistance. That's the basic idea. We can also write this as like delta V over I, right? So they have a lot of possibilities, right? So on the scoring guideline for these, they're not super sticklers when it comes to how you want to represent the data, what you put, whether or not you put the independent variable on the horizontal. If you mix them up, you still get credit for it as long as you do it right. So now, in terms of plotting, well, at this point, this is when I like to show the scoring guideline because that'd be very tedious. All right, so here they did it in terms of 1 over millimeters squared, but here in the calculated columns, they calculate 1 over d squared and delta V over I to get the resistance. And it's very similar to our resistivity lab. The only difference that we had is we had different lengths of wire that had constant diameter. They were both all constant gauge. This one's a little bit different. It's just different diameters of wires, but it's the same process. And then way you measure the resistivity is by getting the slope, right? So we know the slope is 4 rho times L over pi, right? That's that's going to be the slope of our graph, the one that we drew, or the one that we were going to set up. So then if you want to solve for the resistivity, well, then the resistivity is just going to equal to the slope times pi divided by 4L, because L is a constant. And as with all the other graphs, remember the key fact, I mention in every video, that the points you want to use for the slope cannot be data points. All right, they have to be points from the best fit line. So you draw a best fit line through the data points, and then you pick 2 points in that line to actually get it. Did I miss a part? Yeah, calculate experimental value, and then look at all the different possibilities, right? So again, I'd prefer if you set it up in the most reasonable way based on the equation, and that you always put the independent variable on the horizontal axis. But as you can see here, if you don't put the independent variable on the horizontal axis, it's fine. You're not going to, it's not a big deal. As long as you put, the correct dependent and independent variables. It doesn't matter which axis you put them on in terms of the scoring. But generally speaking, you want to put the independent variable on the horizontal axis. Alrighty, almost there. We got one more to do. And this one is another RC circuit. Surprise, surprise. And we have to calculate okay, this one, we have a value of R1 that's increased and the current allowed to reach steady state, indicate whether the new charge in the capacitor is greater than Q naught, less than Q naught, or equal to Q naught. So here, the circuit has been connected for a long time. So the capacitor has already been charged up. And then they increase the resistance R1. Okay, and we have to indicate without whether or not... Okay, so we have to justify it without using the equations. All right, so here's the basic idea. The battery doesn't change, R2 doesn't change, the capacitance of the capacitor does not change, and what happens to the charge of the capacitor? Well, if R1 increases, right, then that means that the equivalent resistance of the circuit increases, but proportionally, the voltage drop across the capacitor is going to have to decrease. And let's try to understand why. So if this resistance R, okay, let's say it doubles. Let's say they both have the same resistance. Well, if it doubles, then this resistance R1 is going to have twice the voltage drop of R2, which means that given that the voltage drop for the whole circuit is the EMF of the battery, that means the voltage across R2 has to decrease, and the voltage across the capacitor will also have to decrease by virtue of the fact that it's connected in parallel with R2. So that's basically the answer. So here it's going to be less than Q naught. Oh, whoops, all right. So we know that's going to be less than Q naught. And then the full line of reasoning basically is that increasing the value of R1, that's going to increase the voltage drop across R1, and that's going to decrease the voltage drop across R2, right? So given that the total potential difference across the whole circuit is just the EMF of the battery, if I increase R1, that increases the voltage drop across R1, which decreases the voltage drop across R2, even if R2 stays the same, because R1 is larger, has to have a larger voltage drop, and the total voltage across the circuit is just the EMF of the battery. And then since the capacitor is connected in parallel to resistor R2, that means the voltage drop across the capacitor is going to decrease. And if the voltage drop across the capacitor decreases, given that the capacitance remains constant, then the charge on the capacitor will also have to decrease. And that's the line of reasoning for part A. Then we have to derive an equation for a steady state charge on the capacitor. And then we have to see what happens when we connect a non-ideal voltmeter. So last circuit I want to show off. Here we go. This is the circuit. So now we have here, it has reached steady state. We see that the voltage across the capacitor is 5 volts. All right, so let's see what happens. If I increase the voltage, if I increase the resistance of R1, that resistor on the top, what's going to happen to the charge on the capacitor? So what's nice is that you can actually visualize it. Let me turn off the value so we can very clearly see it. If I increase this resistance, let's see what happens to the charge. And if you notice, the charge on the capacitor is decreasing. So here we see that the voltage is going to be decreasing. It was previously at 5 volts. And look how little charge is on there. Let me increase the resistance even more. All right, and now my voltage drop across my capacitor went all the way from 5 down to like 0.78. And there was barely any charge on it. And the reason for that, again, is because the potential difference of the battery is what and I think I made it 10 volts in this example. So the potential difference across the battery is just 10 volts, right? So the potential drop in the original resistor, I have both these resistors at 10 ohms. So it drops 5 volts, and it drops 5 volts again, all right, to reach 0 volts, all right? And then the voltage across the capacitor is also 5 volts in this example, all right? But since I increase the resistance of R1, that's going to increase the voltage drop across R1, which then decreases the voltage drop across R2, which in effect decreases the voltage drop across the capacitor. Those two are in parallel. They have to have the same voltage drop because they're in parallel. And if the voltage across the capacitor decreases, then the charge on the capacitor also decreases, as we can see in the simulation. All right, so now almost finished. We need to now derive the steady state equation for the charge on the capacitor. Well, when the capacitor is fully charged, we know that the voltage across the capacitor has to equal the voltage across R2. All right, so here I know that Q is equal to CV, but specifically I'm going to write CV of R2, right? So whatever the voltage is across R2, right? So whatever my delta V for R2 is, that has to be the same delta V as for the capacitor because those two are in parallel. So now I just need to come up with an expression for the voltage drop across R2. So delta V for R2 is equal to the current going through R2 times R2. And I know that the current going through R2 when it reaches steady state is basically the current going through the battery. So the equivalent resistance of these two resistors is R1 over R2. So REQ is equal to, not R1 over R2, R1 plus R2, okay? And then R1 over R2 is going to come up when we look at the current through the circuit, right? So the current through the battery, the EMF of the battery is equal to the current times the equivalent resistance. And I know that the equivalent resistance is R1 plus R2. So that's I times R1 plus R2. And then if I want to solve for the current, I know the current has to equal the EMF of the battery over R1 plus R2. And that's pretty much it. We had to solve for the state of charge. So I have the current here, and that tells me what the voltage across the resistor is going to be. Okay, so now I'm going to go back here. I'm going to say, so from here, from this line of reasoning, I know that Q is equal to C times V, and V for the resistor R2 is I times R2. So I'm going to write C times I, which is epsilon, over R1 plus R2, all times R2. And that's the answer. So that's going to be the steady state charge on the capacitor, this expression right here. And then C, when the circuit's in steady state, a non-ideal voltmeter is connected to the circuit to read the potential difference across the variable resistor. Indicate whether the new steady state charge on the capacitor will be greater than or less than or the same as before the voltmeter was added. All right, so a voltmeter, just so we understand, a voltmeter has to be connected in parallel to the circuit element. An ideal voltmeter has infinite resistance, and the reason you want an ideal voltmeter to have infinite resistance is that you don't want any current to actually travel into the voltmeter. All right, it's because if there's current traveling into the voltmeter, well, then that's affecting the circuit. Now, all real voltmeters don't have infinite resistance, and in effect, they don't really affect the circuit at all, especially if you're dealing with a circuit that has a fairly reasonable current. But, when you start getting into very, 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 very small currents, that voltmeter is going to play a bigger role. So it doesn't actually have an infinite resistance. It just has a very, very large resistance. Okay? So if you're probing circuit elements that have, they also have very, very large resistances, and you're probing very, very tiny circuits that have very, very small amounts of current going through them, then you have to consider that with your voltmeter. But in other words, if the voltmeter has a large but not infinite resistance, then it is in parallel with this resistor R1. And as you know, the equivalent resistance for resistors in parallel is this equation. Okay, so let's say R2 is my resistance of my voltmeter. Well, if it's infinite, then it doesn't really affect my circuit at all, right? Because 1 over infinity is 0. But if it's not infinite, if it's a large, large, large resistance, but it's not infinite, then it does affect the circuit a tiny bit, all right? So that is going to effectively decrease the resistance of resistor R1. Well, not exactly. The equivalent resistance here. So this equivalent resistance of this part of the circuit, all right, so instead of R1, I'm going to put REQ for this part of the circuit. That equivalent resistance will be smaller with a non-ideal voltmeter, okay? So that's the idea. So a non-ideal voltmeter effectively is going to decrease the resistance of this part of the circuit. And if the resistance of this part of the circuit decreases, well, then that means that the voltage drop across this part of the circuit also decreases. And if the voltage drop across this part of the circuit decreases when connected to the battery, then that means the voltage drop across the capacitor has to increase, right? So it's basically the opposite reasoning as from part A, right? So it's asking the new steady state charge will be greater than or less than or the same as it was before the voltmeter was added. And the answer is going to be greater than, because of this similar line of reasoning. The potential drop across resistor R1 is going to decrease. And if that decreases the potential drop for resistor R1, then the potential drop across resistor R2 has to increase because, the voltage drop across the whole circuit is the EMF of the battery. And since the capacitor is in parallel with resistor R2, the voltage drop across the capacitor would also increase. And again, since Q equals CV, that also means that the charge of the capacitor in steady state would increase when you connect a non-ideal voltmeter to resistor R1. So anyways, hopefully that helps. Let me know if you found the circuits, or actually the circuit modeling, if that was actually helpful, because that was the goal. And if you have any questions, feel free to email, stop by after school, during Pride Block, just make sure you have a good understanding of the circuits. And if you need any additional help, don't hesitate to ask. All right, good luck.